Okay, so welcome. My name is Jim Laris. I'm a professor at EPFL in Lausanne, Switzerland. And I'm going to talk about some work that I've been doing over the past couple of years with a postdoc, Nashang, who's actually downstairs giving a talk, and one of my grad students who's sitting in the audience. I'm going to give you a little bit of context about non-volatile memory before we start talking about the research results. Remind you all that back in the good old days when I actually started programming, all memory was non-volatile. So this is core memory, which is a little ferrite disk, little magnetic disk with wires running through them. You send a couple pulses through them on an XY axis, and you can address individual bits. You send the pulse at a high enough intensity, the bit flips based on the magnetization, and then you have to rewrite it to sort of put the data back into the memory. But it was persistent. Basically, you turned off the power, and whatever you left in the memory of your computer was there. DRAM, which is what we use in pretty much everything today, doesn't have that property. You turn off the power, and a millisecond later or so, you've lost pretty much everything that's in memory. All right, background. So the world we live in currently has sort of two types of memory. The processor talks to DRAM over a high-performance bus, quite a bit of bandwidth, pretty low latency. And then there's the non-volatile world, which used to be hard disks and now is SSDs and hard disks. The connection is different. The connection is a lower bandwidth, higher latency. You can't access individual bytes. You typically transfer blocks, which are about 4K bytes, back and forth across this. So these are the two worlds. You turn off the power, and those retain storage. You turn off the power, and DRAM loses with the contents. The interesting thing about non-volatile memory is it bridges the two worlds. So it's non-volatile. You turn off the power, and whatever is stored in there is there. It's also accessible like DRAM on a byte addressable base in an address space over a high-performance bus, the same bus we use for DRAM. So the advantages of it are actually kind of interesting. So one of the things is because it's non-volatile and because of the technologies, it only consumes power during memory accesses. So if you're not accessing the memory, it's literally sort of sitting there doing nothing, and it retains your data, and you don't have to refresh it. So it doesn't consume power. DRAM, on the other hand, consumes quite a bit of power. It has to be refreshed every millisecond or so. Second thing is it retains data without power, and we'll explain why that's interesting in a minute. And then, as compared to SSDs or disks, it's directly byte addressable at a low granularity and low latency. So the three characteristics make it quite different than either of the two storage media that we've used for the last 50 years or so. The interesting thing, it's actually almost available after about a decade of people talking about how it's going to be available the next possible year. Intel is about ready to announce it. They've shown it at a conference. This is a DRAM module that has persistent memory on it. Exactly what it does, I don't actually know. Adam?
I don't know if you're going to get to this, but beyond the granularity of access that the drive supports, what are the performance characteristics of granularity?
Very good question. So the answer is nobody really quite knows because, as they said, this is not really available yet. You can get access to pre-released samples, but you have to sign an NDA. And so even if you had the performance numbers, I'd have to kill you after I told you. And I don't have the performance numbers. Everybody sort of in all the papers pretty much assumes that it's going to be at least several times more expensive, particularly for writes, than DRAM. And so, as you'll see, we'll do sensitivity analysis, assuming the access time goes up to about a microsecond, as opposed to, say, 100 nanoseconds for DRAM.
So I was asking more about the extent to which we need to think about locality in choosing the order that we run operations in. The bottom line.
There's no real locality characteristics to it. I think it's very much like DRAM, where it's organized in a row, where you basically access cache blocks. You take advantage of the whole memory cache hierarchy. And as you'll see, that's part of the problem. Okay, so it's there. So why would you possibly want to use it? Let me give you sort of one scenario which seems quite likely. There are a lot of services that hold a tremendous amount of data in core databases. The reason they do this is for low latency. If you're basically doing a search engine, you hold the entire web in the memory of the computer, so you can do a search query in less than 100 or 200 milliseconds. Similarly, if you're doing a social network, you need the network graph, or at least the recent parts of the network graph, in memory so you can provide performance. And the way this is done is it's split across a large number of machines called sharding, each one of which holds a small segment of it. You broadcast queries to all the machines. They look at their part of the web or the social network graph. So if you have one of these large graphs and you put it in memory, what happens when one of these machines go down? You have to bring it back up, and you have to reload the graph. If the memory is large enough, and people really want to make this fairly large, talk about, say, terabytes, it can take a very long time to recover this data. You have to read it off of a disk. Disks are about a gigabit per second. SSDs are faster than that, but still not significantly faster. The PCIe bus doesn't have unlimited bandwidth. So it can take a very long time to read this back in, particularly if it's stored in an external format like XML, and you have to parse it and recreate the data. So it would be very nice if the machine went down and it came back up, and this graph was still in its memory. So you could just recover quickly, you could bring it back online. So this is, I think, one of the initial scenarios for it. You can probably imagine many other uses for persistent memory, but I think this is what Intel's targeting with their products. So let's talk about how you program it. This is a programming conference, not an architecture conference. How not to program it. So this is the classic example that you use for showing off transactions. So you have two bank accounts and you want to transfer money between them. You take it from one and you put it into the other one. Two separate steps. And what could go wrong? Well, this is actually a little different than what goes wrong if you talk about parallel programming or databases. So let's assume this model. This is at least people's conceptual model. You have a processor and you're talking to NVM. You read the balance from one and you put it into the other one. That doesn't seem too bad. You can imagine that we have the usual transactional problems. If the program stops here, then we may have taken it out of this one and not put it into the other one. That happens pretty much with every sort of persistent store and transaction of this sort. But we have a different problem. This is not actually the way hardware works. So hardware has a cache, and the cache sits between the processor and the non-volatile memory. And caches have replacement policies. So basically, the data that you write into the cache can get sent to main memory by the replacement policy. Replacement policies are not actually specified as part of the architecture. So the hardware can do whatever it wants. Typically, it's some variant of least recently used, but if you have a cache conflict, if it's a set associative cache, you have a conflict that things can get written back to main memory, in this case, non-volatile memory. So that means that we execute these statements in program order on the processor. It writes to the cache in program order, but the non-volatile memory doesn't actually see the effects of these writes in program order. It sees them in, we might as well just assume the worst case, some random order. So we could actually be adding to this balance ahead of decrementing from that balance. And so we can get a totally inconsistent result in non-volatile memory, something that really doesn't correspond to any execution of the program. That's not good. So what can you do? Well, the first thing that people sort of proposed is, well, if the cache is the problem, let's implement some cache flush instructions. So, as soon as we write this one, we basically go and flush it out of the memory. We increment this one, we do another flush. And then on the Intel processors, you have to do this barrier instruction to wait for the cache flush instructions to reach the memory because they're asynchronous instructions. You do this, and basically, yes, these things will get written from the processor to the cache to the memory in the order in which they execute in the program. Problem is it doesn't really solve your problem. Suppose that the program crashes at this point, or a bunch of other points in there, what you find in the non-volatile memory is not necessarily going to be sufficient for you to recover and continue execution.
So far, this seems like what we're used to from programming disks. Is it just going to be that more programmers need to write this kind of code, so we want to work harder to make it easy?
Yes. So it is very similar to exactly what happens with disks. And so if you have an M-mapped memory segment, people typically read things out of mapped memory segments because the exact semantics of what happens with the pages and when they get written back to disk is equally unclear. It's based on the paging policy. So it doesn't get used all that much. In this case, we're giving people a very attractive nuisance, as the lawyers call. It basically looks like memory. It looks like you can just read and write to it, and it should be persistent. Okay, so the other thing that a lot of people have realized is that transactions and persistent memory fit together very nicely. There's a whole slew of papers over the past 5 or so years basically saying, put this in an atomic block, make sure the atomic block does the cache flushes in the right order. And actually, if this is really truly an atomic block, we'll see when we get to look at the details of it, these cache flush instructions can be taken away from the statements and basically associated with the atomic block itself. And so the programmer really just writes this code in black in there, and it looks like things are going to work fine. We'll talk about why it doesn't work fine in a couple slides. Okay, so let me talk a little bit about the usage scenario, the sort of life cycle of NVM. So we have a persistent heap. It contains our favorite data structure, which will be a tree. And we start up a process in the OS. It creates what we'll call transient memory, basically the address space of the process. It'll be in DRAM. We will continue to use DRAM for things like stack and code and all the other things that you have in your program. We'll also then map in using mmap or a variant of mmap, persistent memory. Linux already supports this. The persistent memory is part of your file address space, and you can just mmap it into your address space. We'll see that has problems later as well. But for now, just assume all this works. The program runs, it makes changes to the transient memory, makes changes to the persistent heap, and at some point, the program stops, either because it finishes execution, or because there's a fault of some sort, or because there's a power failure. And then that goes away. But this persistent heap is persistent, and so it stays around. And then we have this cycle where you run, you access the memory directly, you terminate it, and you want to ensure this property that whatever's in persistent memory is consistent. We'll talk exactly about what consistent means in a couple slides. And then we'll have to do something to recover it. We are not just going to be able to directly start up the program and assume whatever's in memory is usable. And there are a few problems there. And then we can just run. And we can just repeat this cycle. It's very common if you have a database to do this. We don't have the layer of software between us and the persistent store that you have in the database. So this is exactly what happens with a database, except that here the program directly accesses the data. It doesn't go through SQL queries to access it. So we have to figure out how to make this all work without that thick layer of software between us and the persistent store. Consistency is an interesting concept. It's been batted around many times in many different contexts. In this case, I'm basically just going to take a very simple definition. It is an operational definition, which works for us. So the program should be able to stop at an arbitrary point. And this is literally between any two instructions in the program's execution. And transient memory go away. And we should be able to restart the program from the beginning, not necessarily at the point at which it terminated. To actually restart at the point at which it terminated, we would have to save a tremendous amount of state, all the registers in the machine, all the transient memory. That would be too expensive. We can't write to persistent memory fast enough to do that. So let's just assume that we restart the program at the beginning. The program knows how to sort of restart itself and look in the persistent memory for whatever values that it needs to restart again. The guarantee we want is that the restarted program will produce the same output as some execution of the program without that termination in it. So we don't get some new bizarre output because the non-volatile memory is left in an inconsistent state and we've added to the bank account without decrementing from the other bank accounts, so our accounts are totally out of balance. That's the property we need to assure that is always true, that we can restart the program and continue execution, and we will be producing an execution that is correct. In general, it's very difficult to ensure this because all of the states the program goes through don't necessarily leave memory in consistent states. That's why we bring in these transactions to ensure that the program appears to move between consistent state to consistent state. We want to capture in the non-volatile heap those consistent states. It's very similar to concurrency. In concurrency, the program stops, the thread gets descheduled, and another copy of the program runs at that particular point in time. It's very similar to exactly what we are having happen. There are a few differences, one of which is this program will never resume after this one begins with recovery. And that has some consequences. Some of the optimizations that you do to increase the speed of parallelization, things like privatization, actually are exactly the wrong thing to do in this case, because once you privatize a state, you've put it into volatile storage, into your registers, into your local memory, and then it becomes subject to loss when the program terminates. But it's very similar in a long sense, which is why the transactions actually work here as well, software transactions. So this is the example we had earlier. Software transactional memory, there are two forms of it, and they'll be relevant in a second. There's the one where you have an undo log. So before you're going to write into the persistent memory, you save the contents of that memory location so that you can restore it if the transaction fails and you have to roll back. So in this case, we were going to write into this location, so we save its contents into the log. We then write into it, and later on, if the transaction commits, we just discard the log. If the transaction rolls back, we restore that location. That's the undo log. The other thing we can do is a redo log, where instead of writing into the location, we write into the log itself, and we do all the calculations using the log. And then when the transaction commits, we copy all the values from there into their final destinations in the persistent memory. Don't really care which one we use. Most people tend to use the first in terms of their implementations for persistent memory. It's easier to explain, so that's what I'll use in these slides. You want to know more details? There's a book. I can recommend it since I was one of the authors of it on software transactional memory. It has lots of details how to implement software transactions efficiently for memory. Okay, that was a long background, but I just want to sort of put everybody on the same page for the talk. So I'm going to talk about three different aspects of how you do this well. And well means you do it efficiently so that there's good performance and so that you can always recover from a failure. First part is efficient logging, which is related to the transactions I just showed you. Then there's another scheme which we have recently come up with, which is a slightly different way of doing logging, which is even more efficient than before. And then there's this question of recovery. What do you do after the program crashes? How do you restore the non-volatile memory to a state that you can use in the program? Okay, so let's look at logging. So here's a log. It has basically a location and the old value in it. And you have a head pointer to the log. And this is just a sort of simple conceptual version of what a log looks like. You write a location and you write its value in there, and then you can go and sort of manipulate the location directly and write new values in there, and you can always restore it by just going back to the log. Okay, and then you increment it. So what could go wrong? Okay, first of all, we have a cache, we have non-volatile memory. The processor writes into the cache. It does not write into the non-volatile memory. So what could go wrong? Well, we could write into this location in the cache. Our cache, of course, has a write-back policy, which we do not control. So it could write back in whatever order it wanted. Notice that here we have an empty log entry because these values have not yet been sent from the cache to the non-volatile memory. And so if we failed at this point and tried to do recovery, we would have to be able to deal with an entry that doesn't contain the right values. So then we write there, and the answer, of course, is what I told you earlier, is you do a cache line flush at a couple of different points in here. So after we've written a log entry, we flush it into the non-volatile memory. We extend this to the next entry. We then do another cache line flush, and both of them stay in lockstep consistency. So at any point, if we have a failure, the log will be in a state that we can use to do recovery. Problem, of course, is that we have two of these cache line flushes. These are synchronous operations. They take somewhere between 70 and 200 nanoseconds to go from the processor to the non-volatile memory to make sure that all the data is actually there, and then to come back and to allow the processor to continue. It's a blocking operation, so basically all of the sort of speculative execution gets stopped, and the processor just sort of sits there waiting for something to come back. It's a barrier. And if you do this all the time, basically every write to memory involves this kind of overhead, then we're running at a greatly reduced speed. We're running at the speed of main memory, not the speed of the cache, which is going to be a major hurdle for us. So what Masstree came up with is a sort of very interesting consistency model. We have two assumptions, one of which is that the processor consistency model that we use for parallelism also applies to non-volatile memory. So basically, if you ensure that two store operations become visible to threads because you've written them into the cache, then the consistency model will carry through to the writes that we're doing with non-volatile memory. So that we can use the serialization instructions that come for parallelization to ensure that writes go to the cache in the right order, which is going to be important to us because if we can't get the writes from the processor to the cache in the right order in spite of compiler reorderings, speculative execution, then we won't be able to do anything there. So we can assume that this is true, that we can force the ordering of store operations using the same mechanism we use for parallelism. The second assumption is actually much more interesting and useful. Cache lines are transferred from the cache to the non-volatile memory as a single entity. The entire cache line is transferred there. So all of the writes that have gone to the cache line at a particular point when the cache line is flushed to main memory will be transferred. And that's a key thing. That means that if we write into the cache line, then all of those writes will be seen. And moreover, we can say that the order in which the writes occur in the cache line will be preserved by the combination of these two assumptions. So we don't need a flush instruction. We just need to guarantee that the store instructions occur in the right order into the cache line, into the same cache line. And then we don't really have to worry about when the cache line gets flushed to memory. It's a little bit restrictive. We can only talk about a cache line here. But it turns out we can do a lot of things with this idea. So let me show you one thing. So in our log entry, we add one more bit to it, or we take one bit from it, and we use it as what's called a validity bit. Basically, one means that the cache line entry, the log entry is valid. 0 means that it's not valid. And it's initialized to 0. There's a bunch of tricks in the paper. We can do that. So in this case, what we do is we assume that if you create a new entry, if you bump the pointer, you'll get a 0 bit. Then when you write into it, it doesn't really matter when it got flushed to non-volatile memory because this 0 bit will be written into the cache line before anything else is written into the cache line. So then we can write the value, we can write the location. This can get flushed to the non-volatile memory at any point because we're writing them in the right order. And then we flip the valid bit after all the data is there. At some point, we do a cache line flush just to ensure that it's in non-volatile memory, and all of it's there with a valid bit of 1. If it gets knocked out of the cache by a write-back policy, by a conflict miss, by something else, it doesn't really matter because the last thing we did was to write the valid bit. So what you will see here is an entry that's partially written with an invalid bit. And so during recovery, we can just ignore it. It requires one cache line flush as opposed to two. And as I'll show you in the slide or two, that actually makes a big difference in performance. Can you find a validity bit? And the answer is almost always you can find a validity bit. Is there a question?
Yeah, I have a question. Did you switch the order of changing the head pointer, or?
I didn't show the head pointer on this, but it turns out it doesn't matter when you do the head pointer on this one because of this validity bit in the value that gets there. So, you know, the head pointer can be done in the wrong order, and there will be an entry here which is pointed to maybe with an incorrect head pointer, but it will have a one valid bit.
With this scheme, is it still true that for every word level write operation, you have at least one cache flush in terms of the programmer experience? No?
For every cache line sequence of for every sequence of writes to the same cache line, you need one cache line flush if you want to guarantee that the contents of that set of writes is in non-volatile memory.
Do you do program analysis to figure out which writes are going to the same cache line?
No, we depend on the programmer to do this. So it's if you're implementing this as part of a software transactional memory system, you know how big your log entries are. You basically guarantee that they fit into there. The paper contains a bunch of other examples with other data structures where we think about it. And you'll see a later example in the next section where we have a multi-cache line data structure where we take advantage of this same property.
Yes, just quick clarification. When you said the programmer has to get it right, you mean this library, the system programmer is building the
Yes,
transactional
in this
memory
case,
system,
in case
not
of,
the application.
yes,
programmer,
in this case, the application programmer does not see this level of detail. Yes, absolutely.
This is just the log.
Yeah, but you know, if you're writing your own data structures to take advantage of this, yes, you do have to get it right. But this is for the log, which is part of the transactional memory system, which is below it. So, you know, if you write atomic around your code, all this happens for you for nothing.
The other question was that you now get a monotonic behavior in terms of the log. There can't be any invalid cache line in the middle of a log, right? So
That's correct.
That's
Yes, that is the property, is that you want to be able to sort of read the log from the beginning to the end, wherever the beginning and the end are, and know that everything in there should be rolled back. Except in the last one may be partially written and have an invalid bit, so the end is one earlier than it looks. There was another question? Great. All right. Can you find a validity bit? The answer is you can almost always find a validity bit. The cache line is 64 bytes. If you're using pointers in there, which we are, you can take bits out of the pointers. The x86 does not really use the upper 16 bits of the pointer yet. There's an extension which is going to use some of those bits, but there's still going to be, I think, 6 bits left unused at the top of the address space. If you have pointers to word-aligned quantities, which you typically do, then you have bits at the low part of the pointer you can use as validity bits. There's also a whole bunch of other ideas in the paper about how to do this if you have non-pointer data. So you can initialize the log memory with random values. The values, if they're for 64-bit quantities, say integers or floating point numbers, the chances of them conflicting with the data you're going to write is actually fairly minimal. It's 1 over 2 to the 64th, so it's probably not going to happen with high probability. And then a flexible validity bit is you can basically look at the difference between what was in memory. You can read the old cache line entry and what you're writing in there, find the first bit that differs, and use that as the validity bit, recording that in the side data structure where the difference is. If there's no place where they differ, it doesn't really matter because you've already written your data to persistent memory in that case. So you almost always can do it. I can't guarantee that you always are able to find it, and it becomes a lot more complicated if you have data structures that span multiple cache lines and you have to do it there. Then it may not be worth it in that case. You may want to do something else. just an example here. So this is basically a memcached-like data structure, basically a hash table to look up values. There are two implementations. The red one is the single trip persistence, which uses the valid bit and a single cache line flush. The blue one is 2 round trips, which is basically the naive version. It does a cache flush for each write to the log. And you can see that depending on the size of the set, for small sets that fit entirely in the cache, you see actually a fairly large performance difference. When the set starts getting bigger and you don't have as much cache locality, then the cost of actually doing the flushes goes down because you have conflicts and some of the data has already been flushed to main memory. And then the question about the cost of it, we added latency here. So this is between 0 and I guess it went up to 800 nanoseconds of additional latency at the synchronization operation to basically take into account how long it takes to write to non-volatile memory. And you can see that, again, the single cache line flush is better, but as the latency starts to get larger, the difference becomes a little bit smaller, but it's still worth doing at that point. And someday we'll get the real memory and be able to do this on real persistent memory. Okay, second slide. So this is more recent work. Most of you probably are familiar with the idea of checkpointing. So with checkpointing, conceptually at least, what we would do is take the non-volatile memory and stop the process from making forward progress and then make a copy of the non-volatile memory so that we could use that for recovery back to that point. It sounds kind of heavyweight and crazy, but it turns out this is actually what is done in high-performance computing. So literally, every n minutes or so, you stop your computation across all the machines, you checkpoint the state of the process, which may take many minutes, and then you continue execution. Because if you have a long-running computation, the cost of slowing it down a little bit every hour is better than having to redo days or weeks of computation. So can we do this? Well, we don't really want to do it this way. The non-volatile memory might be very big. We don't really want to make a copy of all of it. It'll take a long time, and it's really not necessary also. So what we did is we built an example of this using an example of our idea. We don't have the general framework yet, but we do have an example on a very interesting data structure. It's called a Masstree. And it's a combination of tries and B+ trees. It's extremely cache-efficient data structure. It was designed to sort of have very good locality in traversing and doing reads and writes into this index. And it's been used in the Silo in-memory database, key value stores, a bunch of different applications for it because it performs extremely well. So what we wanted to do was make this data structure persistent by assuming that the index, the Masstree data structure, would be stored in non-volatile memory. This paper actually now has been accepted. It'll be in AS+ for it. So one key idea here is an epoch, which basically is an interval of time in the execution of the program. We're using 64 milliseconds. It turns out that you can use values that are smaller or larger than this. Masstree actually uses this for its memory allocation, and so we just piggyback on its interval. We could have made it different, but it's easier in terms of the implementation just to go along with their interval, and it works very well. There's an instruction. It turns out for some reason it's a privileged instruction, but it's an instruction on the x86 which flushes the entire cache to main memory. And in our experiments on our processors, it took about 500 microseconds to do the flush. So half a millisecond to do the flush. If you do the math, if we do it every 64 milliseconds, then we're paying less than 1% of the execution time to do the cache flush. Yes, there is, you have to go in the kernel, but that's all taken into account there. So what's happened after we flush the cache to non-volatile memory? Well, at that point, the non-volatile memory contains the state of the program. We can basically go and restart execution and find it at that particular state. We want to execute this cache flush instruction at a point where that state of the program is consistent, basically when we don't have a transaction in the middle of executing. But that's fairly easy to do, particularly with the Masstree data structure. The problem comes, suppose we're in the middle of an epoch. We flushed the cache at the beginning of the epoch. We've then continued execution. Some of the cache has been modified, some of the cache has been written back to non-volatile memory. What happens then? Well, how do we recover? What we're going to use is something called an in-cache line log. Basically, instead of having a single log data structure like we had in the previous section, we're going to have local logs within the cache lines of the Masstree data structure, which we're going to use to be able to do recovery. And we'll have a separate undo log for the very complicated, relatively infrequent cases. So let me show you how this works. So this is a Masstree node in the tree that it has. It's 5 cache lines long. It's not sort of a single cache line. It contains a number of different fields. There's a sort of key field here, which is the permutation index, which does a couple of things. One of which, it tells you which entries in this tree node are unused. It also allows you to reorder the entries by changing the indirection in this permutation vector. And then we have keys and corresponding values in there. The unmodified Masstree node has 15 keys and values. We took some of the space, and so we're going to have 14. So we're going to have a little worse cache locality than the unmodified one, but not too bad. These green fields are fields that we've added. So basically, this permutation entry right here in green is the log for this permutation value here. So basically, we're going to save the permutation value into here. And similarly, over here, we're going to have 2 entries, which are the logs, which are the log space for logging values here. Notice that we need 2 of them because these are different cache lines. And so this entry will be for values 0 to 6. This will be values 7 through 13 there. We're careful to keep everything in the same cache line because of the property I talked about earlier. So let me just show you a couple examples of how this works. Easy case is, let's assume we're inserting into a tree node and there's an empty slot. The way you find the empty slot is to look in the permutation vector. And then we, of course, will update the permutation vector by recording that we're using that slot. So what happens? So the first thing we do is we write the key into the empty location. We don't have to save anything because there was nothing in there before, so we're not going to restore it. And we write the value into the location here, and similarly, we don't worry about saving anything because there was nothing there. The one thing we have to do is we do have to save the permutation because we're going to modify that. And then we write the new permutation, which basically records that we're using that key in this entry. And so if we're going to do recovery, the only thing we have to do is to restore this field from the value that we saved there. And because these writes occurred in the order of the saving the value and writing the value in the same cache line, we can be sure that we can always do that without doing excessive flushes. We don't have to worry about these values. Whatever's in memory is fine because we can just basically say it's unused by modifying the permutation. Delete, again, it's similar, a little more complicated. Basically, we save the permutation, we write the new permutation. Actually, it's simpler, I'm sorry. We don't even have to save anything because we basically just change the permutation to say that one of the entries is no longer in the key there. So again, if we have to restore it, we just put that value back in that field. Update, again, works pretty much the same. You save the value that you're updating. So then we use one of these log entries here. And we write the new value into the location. And And then, sorry, I missed something on this animation. Then you actually you don't update the permutation in this case because there was already an entry there, and so we just are able to restore it by restoring it back there. There's some additional bookkeeping that tells us that we have to do that, and I'm not going to get into it. That involves this field there. It's in the paper. We can do sequences of operations up to a point. So we only have 2 entries here, and so we can't do arbitrary sequences of inserts and deletes because we will not be able to roll back an arbitrary sequence of, say, inserts and deletes into the same cache line location or updates to the same cache line location. And what we do in that case is we basically just log the entire Masstree node entry into a regular conventional log and then just continue without doing this fine-grained logging because we have a log that we can restore it from. And that doesn't happen very frequent. We also have to do that in the complicated cases where we split a node because we need to insert more than 14 values in it. The log makes it very easy. We don't have to modify the code very much to make that work. Performance. So the blue lines are the performance of Masstree. This is millions of operations per second, so higher is better. The orange value is our implementation with all of the details, all of the features implemented the way I said with logging for the hard cases and the common cases handled with the in-cache line logs. You can see that the performance degradation is roughly, it's 0.5% there to about 11%. So this depends on the workload. Some of these workloads are more write intensive than others. The writes are what caused the problem. Reads don't have any real overhead in our scheme. It's pretty good, I'd say, given the fact that we made a cache-efficient data structure slightly less cache-efficient, plus inserted a fair number of extra operations. We're getting away with a fairly low overhead here. We also looked at adding additional latency. So this is 0 additional latency to the memory operations, and that's microseconds worth of latency. Obviously, the overhead goes up as you would expect it to as you do it, but it doesn't go up a huge amount because we don't do very many synchronous operations where we basically do a flush and wait for the value to come back from non-volatile memory. That's the advantage of putting things in a single cache line, is we can eliminate a lot of flush operations. Okay, third topic, non-VM recovery. So this is actually kind of interesting. There are a lot of papers about non-volatile memory programming and non-volatile memory systems out there. As far as we can tell, most of them only covered a piece of this problem because there aren't any real NVM systems that people are using. So what happens? Well, we have an OS process, it has DRAM, it has non-volatile memory, it's address space, and then all of a sudden we want to restart it. Well, there are a lot of things that can be different when we restart it. So for instance, your code could be at a different location than the last time you accessed NVM. And there are a lot of ways this can happen. You could have upgraded your operating system. You could be running a new version of the program. There could be the address space randomization that happens for security. Why does this matter? Well, you may have pointers in here, particularly if you have objects. Objects contain a method table. The method table contains pointers into the code segment. You move the code around, and those pointers are no longer valid. Everybody assumed that didn't happen. Another thing that could happen is the NVM could be mapped back into your address space at a different location. So mmap doesn't guarantee that it will map things into the address space at the same location. It may be impossible. Maybe your address space is just laid out differently than it was last time. And if you look at all of the papers, all of the systems that are out there, basically they say nmap using this fixed address, and if it doesn't work, fail. That's not a really good answer. So the key thing is that the persistent data has to be consistent in the recovered process, regardless of what happened to the recovered process, not just in the original process when it failed. So it's one thing to get the data correct so that what's sitting in NVM is consistent. But when you load it back in, it also has to be consistent with the state of the OS and the DRAM that you're using. There are a lot of things that also can go wrong. So within your data structures in non-volatile memory, you can have transient data. You could store a TCP socket or a lock or a thread ID, all of which is very process specific. You restart the program. None of these have any meaning, but they look valid because they were valid in the last execution. You might say, why store them in there? The answer is very simple, because it's good to have all the data local. You could have all this stuff sitting inside tables in transient memory, but that would cost an extra lookup every time you wanted to get access to it. It's not worth it. So the solutions that people had previously were ignore the problem, and basically, they weren't building real commercial products out of NVM because there was no commercial deployment, so it was fine for research papers to ignore the problem and say, whatever. And the trouble is that this is where you store your data. It basically says that your data is no longer accessible if you ignore the problem and one of these events occurs. The other one that's been looked at in a couple of papers is to solve part of the problem. It doesn't deal with the pointers to functions, but it deals with pointers within NVM by saying, well, let's use offsets between the persistent objects instead of pointers. And you can do that. The problem is, of course, you have to write your code using a macro for every reference because, the C code uses pointers, not offsets. So somebody has to do that fix up, and that requires an extra add as well. So it's slower. We've implemented an extension to LLVM, which gives you a bunch of features to make this recovery work much better. So one thing you can do is you can mark fields within an object or a struct as transient, which basically says when you recover, the value in that field should be zeroed. You should just store it away. This is a mutex lock. It's not going to be useful when you recover the program. We also define what we call a reconstructor method, which is like a constructor, except it gets run when you reconstruct the persistent memory. And so it could do things like allocate a new lock for you in the current process so that you could use that value. And then we have a new and a delete operator. So the idea for reconstructing an object is that we have a sea of objects in persistent memory. We have pointers to them which we can find. The way we find them is we basically put a type header ahead of the object saying what type of object it is. The compiler does all this for you. You never see this in your program. And then when we're doing recovery, the first thing we do is we zero all the transient fields by the declarations that you gave us. We worry about relocating pointers to other objects within inside the persistent memory, so we know where all the objects were. We know how to find where the new ones are, and we fix up the offset so it points to the current value. And we do that similarly for methods in method tables, function pointers in these objects as well. A lot of bookkeeping. And then we run the reconstructor function after things are looking pretty good, and that can allocate, for instance, a new lock, if that's what you want to do. Similar to garbage collection, similar to relocation and garbage collection, except it's a little bit more challenging because in doing this reconstruction, things can fail partway through the reconstruction. And so you can be left with this address space that is a combination of the original execution plus partially fixed up. And you have to do the bookkeeping so that in spite of a series of failures during reconstruction, you can bring it forward into a consistent state that you could actually recover from. So this example sort of works through, but basically there's a lot of bookkeeping to keep track of whether an object has been fixed up for the current execution or not. The other problem we have is that it could take a very long time to do this for a large address space. Terabyte address space, several terabytes, it could take a long time to go through it. So we use lazy reconstruction. We do the sort of common trick. We turn off access to all the pages there. On the first access to a page, you basically get a fault, page fault that brings you into our system. We go and fix up all of the objects on the page. We then restart the instruction and things continue. That turns out to sort of be lazy, and it is exactly what people who are building these systems want in practice. They want to be able to turn on the machine and start servicing requests right away, even if the performance is degraded for a small amount of time as you start accessing data and having page faults. Turns out that this works pretty well. So you can see here, this is time in milliseconds. So once we start, this is the number of operations. There's a little point to the program where we're basically getting started and we start having page faults occurring. And then after that, as you access different parts of the program behavior, you have a slightly jagged curve. But the overall performance is very close to what you would see if you had fixed up the entire memory. So it works quite well. And it saves a lot of time compared to doing eager reconstruction and doing the entire memory at once. So, just to finish up, NVM is not the solution to the world's problems, but it is the solution to some of the world's problems. It's a large, persistent, directly accessible memory. I think that people will find a lot of uses for that, particularly in data centers. Programmers, however, can't treat it like memory or DRAM, the memory that we're all used to. You have to be aware of the NVM-ness of it. Otherwise, you can write into it, but you may not be able to use it after you restart your program. You may find what's in there is not what your program actually produced in terms of an execution. The caches are the problem. They make things expensive. You could imagine some changes to the hardware of caches for NVM. It would make this easier where you sort of did total write ordering for cache misses, cache write-backs, and then some of this would go away. Intel may someday do this, but I think that there are a lot of processors out there that are never going to have that. Key thing in terms of all this work is how much can we put into a cache line, and how do we take advantage of a cache line? And it turns out you can put an awful lot more into a cache line than you thought of before. And if you can take advantage of the fact that you don't need to do flushes between writes to words in the cache line. And then the final word of advice is don't forget the recovery, because if you do, you're going to be stuck with a lot of data that's in persistent memory, but it's not useful to you. So that's it. I had a few questions. Are there other questions?
Yes, so if anyone has any questions, I'm going to be passing the microphone around to the speaker.
How would it simplify your life as the author of this system to have particular reasonable changes to hardware?
It would simplify it quite a bit. So, if you had total store ordering or something similar to it on cache line writes, which I think is very hard actually to implement efficiently in the cache, then all of the flushes that we had would pretty much go away, because the writes that you did to caches would then be there. And so you wouldn't have to worry about as many flushes. You could basically just implement the logging scheme like we do for logging for parallelism, and it would be much simpler for that. Programmers could also not worry about it as much. But the in-cache line logs, the rollback scheme that we had, still would be a useful scheme to be able to sort of save values, because you still have this notion of a transaction of some sort that you want to be able to recover from. And I think the epoch-based recovery is actually a very good way of doing it without requiring programmers to stick atomic blocks in all their code. So the answer is maybe. Steve.
Yeah, Steve Blackman, ANU. One thing that strikes me whenever I read about this work, this huge sea of work that's happened in the last 5 years, particularly in the systems community, is the heavy focus on using an unmanaged language like C. And a lot of the issues that come up are probably tied, there are many issues that are tied up with the fact that it's not memory safe. You don't have a memory safe language. You can't abstract over a bunch of things. You could abstract over if you had the right level of abstraction in your programming language. And there's a literature back 20 years ago in the persistent programming language community that did some stuff down this line. But I do understand why people are using C, but I just wondered if you had any thoughts, particularly given that we're here at UPSLA, if you have any thoughts on programming languages and...
I think it's a crazy idea to use a high-level language for writing systems code. You know my thoughts on that. No, actually, it's a really good question. It's something that we actually gave some thought to. And there are a couple of papers on doing Java and non-volatile memory. And actually, I had a paper you know about from Microsoft about sort of using garbage collection to work around failures in non-volatile memory, because one of its shortcomings that I didn't really get into is that it doesn't have the right endurance of DRAM, and so you're going to see cache lines eventually wear out. And so we looked at sort of using garbage collection to work around holes in your address space. But yeah, I actually think it's a really good idea, and I can point you to a couple of papers where people actually sort of thought about doing the transactions for Java. They didn't think about all the other sort of issues in terms of recovery and so forth. And I think those are also sort of bookkeeping issues, but I think important issues as well.
This is a highly hypothetical and somewhat tongue-in-cheek question, but bouncing off the earlier question about hardware, the points that you brought up about like having swizzle pointers and stuff like that, does that suggest a move back to something like segmentation? Because if we run the burrows, or even 32-bit x86, it's a non-problem.
That gets rid of one problem. I talked about a lot of problems, but yeah, actually, if you look at the paper, we do point out that if you use the offsets between pointers, you're basically doing a software implemented version of segments. And so yeah, if you had hardware support, you could just do offsets, and then yes, recovery would be simpler in that one dimension. But you still have the same problem. What are you going to do about the functions? What are you going to do about transient data in there? So yeah, it's also, but that fixing up that stuff is a load of bookkeeping, and it's a pain to get correct. But it's not the worst part of the whole thing by far. So yeah, I could give you other arguments, stronger arguments for putting segments back in machines, but I don't think this is it. Other questions? Good.
Okay, then I think we should thank the speaker once more.